Welcome to part 4 of the solar cell series. By the end of this video, we'll verify the extractor and export the model into LTspice as a drop-in block. Since we've gone through the extractor and cell classes already in the previous videos, only 2 classes are left for the base project, cell synthesizer and test bench cell. And everything that's grayed out represents the thermal and stack layers that build on top of the base. Cell synthesizer is the counterpart to cell extractor, but at this level of the project, it has minimal functionality. Like cell extractor, it creates a cell instance, but in the opposite direction, from the forward model parameters. For now, cell synthesizer is a wrapper for the cell class. It keeps the architecture consistent as we build up to the thermal and stack functionality. The code skeleton only has the init function that creates the cell instance. It can also hold helper functions for things like printing. The main purpose of the synthesizer is to generate reference cells with known answers that cell extractor can be verified against. TestBench cell runs that verification process. Verifying the extractor takes more than a hand-built example or a few datasheet cells. We need to generate large numbers of synthetic cells to test against. That's not a problem because the extractor and forward model are fast. Running 10,000 cells through the verification process takes about 10 seconds. So volume isn't the constraint. Generating random values is straightforward, but those values have to produce a physically realistic cell. The workflow starts by choosing the nominal temperature, the cell material, a photogenerated current range, and the WOC range. These are used to instantiate the test bench. The material chosen sets the bandgap value, and WOC is the bandgap voltage offset. WOC is used because it provides a simple way to apply the same numeric range across different solar cell materials. In the example table shown, the range of 0.3 to 0.55 yields realistic open circuit voltage ranges for 4 different materials. After the test bench cell instance is created, the second phase is running the sweep. The sweep function takes a list of series resistance values and a list of shunt resistance values and runs a loop that creates test cases. Each Rs-RSH pair produces 1 reference cell. For each case, WOC and the photogenerated current are randomized from ranges defined during construction. The ideality factor N is also randomized from a preselected range based on the cell material. Once these random values are chosen, the saturation current I0 is computed from the solar cell equation at open circuit. The open circuit voltage then ties back to every other parameter, keeping the cell self-consistent. Because I0 can vary across many orders of magnitude, this approach helps keep the cell parameters physically realistic. At this point, TestBench has the complete 5-model parameter set, and cell synthesizer can create a reference cell. The reference cell runs the forward model to obtain its cardinal points. As each reference cell is generated, TestBench hands the 4 cardinal points to cell extractor. The extractor runs and creates a new cell object with estimated values for all 5 model parameters. It does that with no visibility into the reference cell's actual values, which makes it equivalent to extracting from a datasheet. The model parameter solution is not unique, so the 2 parameter sets, one from the reference cell and one from the extractor, aren't expected to match. The information we have as input, 3 operating points on the plot, limits full recovery of the real device parameters. And matching the physical device exactly isn't the goal. What matters is terminal behavior, reproducing the curve or outputting the right current at the right voltage. That makes cardinal point match the verification metric. After extraction completes, the extracted cell runs the forward model to produce its own cardinal points. These can be compared to the cardinal points of the reference cell in order to evaluate the performance of extraction. You can also check model parameter match, but it can only be a diagnostic, mainly to confirm that values are reasonable orders of magnitude. We also want to make sure that the solver converges at a very high rate. With this solver, non-convergence usually points to an unrealistic or inconsistently generated cell. As an example, one condition that can cause convergence failure is when the short circuit current multiplied by Rs exceeds the open circuit voltage. Any case that fails to converge is counted as a failure and reported along with the largest cardinal point error. That's the verification approach at a high level. Looking at the code structure, TestBench cell is organized into 2 classes. The first one is TestBench helper. This class is the basis for all test benches, including those for stack and thermal versions of the solver. It holds shared functions and variables that handle parameter synthesis we just walked through. There's a resolve function for each of the synthesized parameters: open circuit voltage, photogenerated current, and ideality factor. The function to compute saturation current also lives here. When running multi-seed tests, a reset function brings the test bench to its default state. The second class is the test bench cell itself, which inherits from test bench helper. Once the instance of the class is created, the sweep function is called, with lists of desired Rs and Rsh values passed in. The sweep function then calls add random case, once for each Rs-Rsh pair. Add random case uses the resolve functions inherited from the helper and then calls add case. Add case is where a cell synthesizer and cell extractor are used, and the results, in the form of cell objects, are saved. Finally, the compute errors function can be used to check the accuracy of the solver. The generation, extraction, and comparison are all kept in one test harness, so scaling from one test case to thousands is just a longer pair of lists. That covers all of the math and code behind the cell extractor and its verification. With the model verified in Python, the next step is getting it into LTspice so that it can be used inside of an actual circuit sim. The schematic for the solar cell model in LTspice is the same diagram that we've been working with, just with 2 ports added, the anode and cathode of the cell. The extracted model parameters are passed in as .param values. The photogenerated current Rs and Rsh values are used directly, with some default values shown here. The diode gets a .model statement that's defined with I0 and N values. Rs in the diode model is unrelated to the series resistance that we've been talking about. That field is the diode's own internal series resistance, and the cell's Rs is R1 out on the schematic. The diode's Rs is set to a tiny value, so it has no impact on the model. Tnom is the nominal temperature of the diode, and in order for the cardinal point results to match the Python model, set it to the same value that extraction was performed at. This is actually one of 3 temperature settings in LTspice, and we'll talk about them in a sec. First, a 2-terminal symbol should be created to wrap the circuit. You can use the hierarchy feature for this. It lives in the dropdown in the menu bar right next to File and Edit. For a hierarchical symbol, leave the prefix blank in the symbol attribute editor. Once you have the circuit and symbol created, it can be dropped into any LTspice sim. Let's go back and highlight some of the temperature settings in LTspice that influence sim behavior. These have to line up with the temperatures used during extraction. Each temperature setting affects the sim differently, so this is a common reason results don't match between LTspice and Python. The 3 temperatures that can be controlled for the circuit are the global sim temp, the nominal diode temp, and the operating diode temp. The global temp is set with the .temp command and defines the default operating temperature for the simulation. The nominal diode temperature is set inside the .model definition for the solar cell diode through the tnom parameter. This is the reference temperature for the diode parameters extracted in Python, so it needs to match the temperature used during extraction. Then there's the actual operating diode temperature, which is set in the instance of the solar cell diode itself. You can bring this window up by control right-clicking on the diode. Then in the row named spice line, set the temp equal to the parameter tsolarc. This allows the solar cell diode to operate at tsolarc instead of automatically using the global .temp value. One other thing is that the Python code uses Kelvin internally, but for LTspice, temperature needs to be set in Celsius, and 25 degrees C is 298.15 in Kelvin, not 298. So don't be like me and spend 2 hours looking for why the numbers are just a bit off. The benefit of all these temperature options is that the solar cell's temperature can be set independently of the rest of the circuit. In the spacecraft, the solar array will be at a different temperature than the electronic boxes, so this is a useful feature. Now we can validate the LTspice model using a space silicon cell example. The datasheet gives current per unit area, so I picked a cell area that puts IMP at 1.5 amps. That ended up being 34.25 centimeters squared, which is a reasonable size for a single space cell. Since current scales with area, the choice doesn't really affect the comparison. The upper circuit contains the solar cell model built from the parameters extracted in Python. Model parameters are passed in through the symbol. V1 is used as the cell's load, and it's swept using a DC sweep simulation command. That's what generates the IV curve. The sweep goes just a bit past the expected open circuit voltage value to make sure that the zero current point is included. And we've seen the resulting curves before. All the plots shown in the previous videos came from this LTspice sim. To complete the circuit, the 3 temperature settings from the last slide are all set to the extraction temperature, 25°C. The lower section holds the reference cardinal values, which we're calling truth. These are the values from the datasheet. Adding some .mesh commands gets model results automatically, instead of chasing each cardinal point with cursors on the plot. If you set these up, the results can be found under View, Spice Error Log, after the sim finishes running. This table is set up to compare performance, so let's see how we did. Every cardinal point matches to within a few thousandths of a percent. That tells us 2 things. First, the extracted parameters reproduce the datasheet cardinal points in a simulator that shares no code with the extractor. Second, the LTspice implementation is wired up correctly with the same diode parameters, resistance values, current source, and temperature settings. So at this point, we've gone from datasheet values to extracted model parameters to a reusable LTspice solar cell block that can be dropped into a larger circuit simulation. This was a large build, but it gives us the core workflow for the rest of the project: extraction, verification, and LTspice implementation. Everything on this diagram is now in place for the cell. The synthesizer generates reference cells, the test bench verifies them, and the extractor pulls parameters out of the datasheet inputs, and the cell class turns those parameters back into a curve. From here, the stack and thermal layers inherit from these same base classes. The single diode equation doesn't change. A stack just puts cells in series, and the thermal layer adds temperature dependence. But at this point, the cell model is done. You can reproduce an accurate solar cell model from just 4 operating values on the datasheet. Thanks for watching.